So we saw an example of factoring in my Keys to Math Success. But factoring, there's a bunch of different ways it can go down. We have our greatest common factor factoring, which is what we talked about before, when we're just looking at a number of terms. And here's a mathematical term, right? Terms. Terms are things separated by addition or subtraction. So we could have something like 3x squared y plus 6x minus, I don't know, let's make that an x squared, plus 12x, or minus 12x. So in this case, we have three distinct terms, three distinct things separated by addition and subtraction. Within those terms, they have multiple pieces, which we call factors, right? So in this case, we can break this down. There's a factor of 3, an x squared, and a y. We can even break down the x squared further. There's two x's that are factored to make that x squared, right? Those are the two factors of x squared. So there's a lot we can do there. I don't need those factors. When we're talking about the greatest common factor, we're going to look at each and every term of an expression, and we're going to see what they have in common in terms of factors. So I guess it might be helpful to have these silly lists. So these are all the factors of that first term. Oops, I guess I need to break down that 6. 6 can be factored into 2 times 3. And x squared is x times x. And then we have, in order, a 2 times 3 times x. And you might remember doing factor trees back in the day for something like 12, thinking of two things that multiply to 12 and continuing to break stuff down until you are at prime numbers. So in this case, those 2 2's and a 3. Again, not a huge deal. We will get to see this, and I don't think there's anything as challenging as this problem within trig, but when you get to pre-calc, this is probably a skill you want to have refreshed. So when we talk about greatest common factor, we're looking for things that are in common. So we can see here, every single one of these terms has a 3. And every single one of these terms has an x. So that's our greatest common factor. We can pull a 3x out of each and every term. I'm sorry. All right, and then we have what's left over. So in this case, if we factor out the 3x, there's still an x and a y here. Because remember, if we want to clear parentheses, we distribute that factor that's in front to each and every term. So if we re-multiply this, we'll come back to our 3x squared plus y. There's still a plus. The next one, there was a 2 and an x. And then there's still a minus, and we have a 2 times 2. So I'll just change that to a 4. So we can always check our factoring by simply distributing back to the other equivalent form of this expression and seeing 3x times xy. Well, that'll give me 2 x's, right? So x squared y. 2 x's was not a good way to say that, but x times x, which is x squared. Here we'd end up with 6x squared and then minus 12x, which is exactly what we started with. So we can use distribution to check our work with factoring. So the other piece of factoring is dealing with especially quadratics. Sometimes we end up with things that are a little beefier than a quadratic, but most of the time, especially in trig, we're going to see quadratics. We're actually going to see things that are what we would call reducible quadratic. They look like a quadratic, but they're not technically a quadratic by the definition of a quadratic. So a quadratic is something that has an x squared term. It only has one type of variable, so the previous question, even though it has an x squared, is not a quadratic because it has that y. In fact, we would call this previous example that we just did, this is a polynomial with degree 3 because we add the degrees of both of the variables. So the 2 and the 1, that ends up being a degree 3. Quadratics are degree 2, and they only have one variable. So typically, we'll use something that looks like this, ax squared plus bx plus c to give us the standard form of a quadratic. The only requirement of this is that our a does not equal 0. Because if a equals 0, we just have a linear term, right? We just have bx plus c. This wouldn't be there, and so there really isn't a whole lot to talk about there. Oh my goodness, I thought I had an undo button, but I lost it. Do I? Nope. I'm going to have to just delete that carefully. All right. So here's what we're looking at. Now, any other term can be 0. So let's just talk about those different cases. So the case when c is equal to 0, then we're going to end up with, and I'll just make up a silly example, let's say 14x squared plus 21x. So c is 0, there is no constant term, but we have that squared term, and we have that the x term, the linear term of our quadratic. So if you end up with a c is equal to 0, this is just a Gcf factoring situation. There is no c that's holding us back. We're going to see when c is equal to a number, we can't take out things. But in this case, it's very similar to our previous question. We could recognize that both of these terms are divisible by 7, and they both have an x. So we could pull that out, and we end up with 2x there. We're basically just dividing this out. 7 goes into 14 twice. X times x will give me x squared, and then plus 3. And again, you could check your work by factoring out. Now, there's nothing in common between the 2x and the 3, so we know we're done. And I'm going quickly. I have a bunch of much slower how-to videos. If this does not make any sense to you, feel free to watch those. I just want to give everyone kind of an overview of what matters and a quick review of all these different cases. So, cool. Now, what about the situation when b is equal to 0? Because these are both cases where things are a little bit easier. So again, I'll give you an example. We'll just go ahead and start with an a of 1 for this. Let's do x squared minus 9. So you may remember this as the difference of squares. If not, it's okay. It's not a rule. It is just a natural thing that happens. If we take something like a plus b and we multiply it, but we're going to be called, what we're going to end up calling by its conjugate, which is a minus b. So same terms, just changing the sign between them. What happens when you go to distribute or FOIL this out is you end up with a squared plus ab minus ab minus b squared. And so these two middle terms, they cancel each other out. And what you end up with is what they call a difference of squares. So again, it's not a rule, it's just something that follows from multiplying two conjugates together. And it's a trick that we use a lot in algebra to rationalize denominators, to deal with complex numbers. There's a lot of situations where we do this in order to clear something that is not great unless it's squared. So complex numbers and radicals being the two situations where if it's squared, it becomes a lot easier to work with. So anyways, if we recognize that something has this structure, it has an a squared, it has a term squared and another term squared with a minus between them, and that's crucial, that minus. Whoop, whoop. So in this case, we can see obviously x squared is x squared, and 9 is 3 squared, then we can use that fact about the difference of squares, the fact about these conjugates, to factor this. So in this case, this thing will become x plus 3 and x minus 3. Because that way we'll end up with the x squared and that minus 9, but the 3x and the negative 3x will cancel each other out. Try foiling this out to check for yourself that this is what happens. So with b is equal to 0, that's typically the only way to solve these, right, is if it ends up being a difference of squares. They can be more challenging. You could have something like 4x squared minus 25, right? In this case, we have to recognize that in order to get 4x squared, we needed to take 2x and square that. So the 2 times 2 gave me a 4. So this is 2x plus 5 and 2x minus 5. But that's it. If there's a plus between them, it is prime. It does not factor. If they are not perfect squares, it does not factor. There is one situation that would fall under that they would factor, and that's this difference in sum of cubes. Turns out cubes also have a cool property with them. It is not something we're going to talk about in this class, and I'm not going to waste any of your brain space on it right now. So let's talk about the general last one, right? When nothing is 0, when you got to factor this thing straight up. So I'm going to give you a is not 1, because if you can do a doesn't equal 1, you can do a equals 1. So let's deal with a is not 1. I'm going to grab one of these questions from Delta Math. A is greater than 1, level 2. This doesn't feel like a level 2, but I'll do it. let me scroll on up. So let's do this. 3x squared plus 5x minus 2. I'm going to talk about why it doesn't feel like a level 2 really quick too. So first and foremost, the way to get a quadratic is to if it factors, is to multiply two binomials together. And by binomial, I mean we have two things very similar to what we dealt with here, right? This is two terms multiplied together. That's how we end up with a squared. And the first one has to have an x. The second term has to be constant. That's how these work. So if we want to get this, one option is guess and check. Guess and check can be great. It really helps build up your, what am I trying to call it? Like, this is a pause for me thinking. Like your number fluency, like just your ability to work with things and see those patterns. It really is helpful. I credit a lot of my own ability to break these things down on the fact that I didn't know there was a method other than guess and check until I taught. Until I was an actual professor. So I went through all of my math career not knowing I could do anything other than guess and check. And I'm sure I was taught how to do this without guessing and checking, and I just didn't pay attention because that's the kind of student I am. So the thing is, what we always notice about these particular binomials, when we multiply them, the only way we're going to get the x squared is from multiplying the first terms of both binomials together, that f of the FOIL. That's where you get the x squared. Everywhere else, you'll just have either an x or a constant. So we know whatever's here and whatever's here, they need to multiply together to give me 3x squared. And in order for them to be binomials, they both have to have an x. Here's why I think this question is easy. We know that 3 is prime. So the only options here is this must be a 3 and this must be a 1. That's it. There's no other way to get to that particular solution, right? When we distribute this out, we need a 3x and we need a 1x. And I don't have to put the 1 there, but I'm doing it for completeness here. Now the other piece is the only way we're going to get the constant is by multiplying the constants together. When we do the inner and outers, we end up with an x. When we multiply the last term of each binomial together, that's the only way there are no x's, we end up with a constant. So we know whatever's here and here, when they're multiplied together, they must equal -2. And again, I'm going, this is an easy problem to me. And I realize that that's a jerk thing to say, something is easy. But this is a good question for guess and check because 2 is also prime, right? The only things it can be are 1 and 2, and one of them has to be negative. So, unfortunately though, we have 4 different possibilities. Oops, that's a giant-ass pen. I don't want that. We have 3x plus 1, 1x minus 2. We have 3x minus 1, 1x plus 2. And then we could also have the 2 in the different place. Plus 2, 1x minus 1, and 3x minus 2, 1x plus 1. So you can see 4 options. Not super hard in terms of checking, and this is where that pattern building understanding really comes into play. I know I want the answer for the middle to be a 5x, and it needs to be positive. And I realize that the way I'm going to get this middle is to multiply the outside terms, the 3x and whatever's here, and the inside terms. And 3x is a hell of a lot bigger number than 1x. So I know, this is again from me playing with patterns so much, I want the positive number here. Because I want whatever is positive times the 3 so that I can end up with a positive 5. And I also realize that if it's just a 1, that's not going to be enough. So I'm going to put the positive 2 here, which means the negative 1 has to be there. And then I can double check. That's a negative x and a plus 6x, which together give me a positive 5x. So that's one method, guess and check. It's awesome if your first term or your last term, especially if both, are prime or numbers with not very many factor options. So I'm going to try a different solution, a different problem on Delta Math and hope it gives me something harder. Yes, give up. Okay, I don't care. Next problem. Oh, my husband's already home. Shoot, that was slower than expected. All right, this next one's going to be better, but I will pause and come back.